Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe a quantity called electric flux. Now, before we get into what electric flux is, I've got a more physical example that I'd like to talk about. So imagine we've got this river. So this line represents the bottom of the river. This represents the surface of the river. We've got this young lad here named Timmy, maybe floating down the river in his boat here. Now, if I were to measure the water velocity at any given points, maybe here, 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 and here, right? Those could be described with a vector pointing to the left, and these vectors would describe how fast the water is moving. Now, we're going to assume in this example that these are all moving at about the same rate. The water moving here is about the same as the rate is about the same as here, is about the same as here, and so forth. It's not important whether these vectors are the same or not in this example. And what I'd like you to focus on is this, right? Imagine I've got like a hula hoop that is in this river. You'll notice that in the orientation I have it shown, those velocity vectors are going through the hoop, right? Well, that means we've got water going through the hoop, and that's an example of what's called a mass flux. The mass flux would describe basically how much water is going through that hoop every second. Now, it's really important to understand, what that depends on. Well, the first thing to realize is this. Imagine that I take that hoop and I rotate it to something like this, so that the velocity vectors are basically tangent to the area there. Basically, little or no water would be going through that hoop. Now, as I rotate the hoop into an orientation something like this, now we've got more water going through it, a little bit more, a little bit more, a little bit more. The maximum amount of water going through that hoop occurs here, where the velocity vectors are making a right angle to the plane of the loop. Now, other ways that I can affect the amount of water going through that hoop, well, I could maybe change the hoop size. If the hoop gets smaller, there would be less mass going through it. As the hoop gets larger, there would be more mass going through it. Then the third way I can affect the amount of water going through that hoop is if, somehow I could make these velocity vectors larger. Like, if the water speed increased, that would increase the mass flux. So again, the important thing to realize, let's sort this out. The mass flux depends on the orientation. Oops. And what I'm going to do is I'm just going to say angle. I'm going to put an angle theta. It depends on the area of the hoop. The bigger the hoop, the more mass is going through the hoop. And it depends on the velocity of the water. Right? I can affect the mass flux any one of these three ways. So I want everyone to keep this example in mind when we talk about electric flux. Alright, I'm going to get rid of this. Including that. Alright, so electric flux has to do with vector fields. Right? So we're going to imagine we have an electric field vector somewhere. And I'm going to go ahead and put a vector here to represent it. Right? So imagine we've got an electric field vector. Now imagine we have some sort of small little area here. Okay, now, oops. So this electric field vector is effectively going through the area. Now you notice that the angle between the electric field vector and the plane here is not 0 or 90 degrees. So what I'm going to do is I'm going to put a vector this way in green. I'm going to call that the normal. And that's going to be a unit vector. So this little caret symbol means unit, and it's at a right angle. That's why I'm calling it a normal. You'll notice that there is an angle now between the electric field and the normal. When we calculate what's called the electric flux, here's what we do. The electric field vector can be broken into components. We've got one component this way in the direction of the normal. Then we've got another vector component to the right. That makes a right angle to the normal. So I'm going to go ahead and give these directions. What we call the electric flux, it's usually represented with the Greek letter phi. it's equal to the component of the electric field that's perpendicular to the area multiplied by the area. That's this vector component times this area. Now, this component, which is perpendicular to the area, you could also say that, call it the electric field parallel to the normal, is adjacent to this angle theta. So when we calculate the flux, it's going to equal the magnitude of the electric field times the cosine of the angle theta, gives the component that's going through this area, times the area. When I write this in class, typically what I write is EA cosine theta, where the theta is the angle between the electric field vector and the unit normal. So that's what electric flux is. I want to talk a little bit about, what does it describe. So if we have a region in space where there's an electric field, in this case, I'll go ahead and be kind of consistent with this. We could describe that with what are called electric field lines. So I'm going to go ahead and draw electric field lines. Now in this example, imagine we have a nice uniform electric field pointing kind of up and right. Again, if you're not familiar with field lines, go back and review my video about electric field lines. Now, if you take a look at this dashed surface here, well, let me make it so we can see it. Let's make it green. And I take this surface and I move it into this region where there are field lines. The flux through that surface describes basically the number of field lines going through that area. So that's what flux is a measure of. It's a measure of the number of field lines going through a given area. Now it's important to realize, though, that how many field lines you draw, in a sense, is somewhat arbitrary. So when you calculate a flux and you get something like, let's say, 7, that does not mean that you have 7 field lines going through the area. What it means is that you have a number that's proportional with respect to your picture to the number of field lines going through the area. Now, in this example, you'll notice that if I orient my hoop something like this, there's basically no flux. The flux is a maximum in an orientation maybe something like this, and in an orientation like this, it's somewhere in between. And again, even look at the picture. Notice how I've got basically 3, almost 4 lines going through that area. Now I've got maybe 3, 2, and none. So that's what the flux measures. It's the measure of a quantity that's proportional to the number of lines going through a given area. And this is how it's calculated, EA cosine theta. Let me talk about its units. So the electric field has units of Newton per Coulomb. Area has units of square meter. Cosine theta is a dimensionless quantity, so flux has units of Newton meter squared per Coulomb. I'm going to go ahead and save example calculations for another video. I just wanted this to be kind of a short introduction to electric flux and how it's calculated, and at least give you a reasonable start as to understanding what it tells you, and that's basically number of field lines going through an area. Hope this video helps. Have a great day.